Assalamualaikum warahmatullahi wabarakatuh and good day. In this video, we will use transformation method to find the function of random variables. But in this case, we will have multi-variable. Okay, so we will use transformation method using Jacobian. So we focus on the bivariate transformation method. Suppose that you have y1 and y2 are continuous random variable with joint density function of this one. Okay, this is the joint density function of y1 and y2, and that for all y1, y2 such that greater than 0. So you have u1 equal with certain function and u2 you have certain function. Okay, and this function you have two random variables. So it's a one-to-one transformation method, which is from y to u. Okay, from y1, y2 to u1, u2, and then the inverse you will have y1 equal to h inverse 1 u1 u2 and y2 equal with h inverse 2 u1 u2. So if you remember in the transformation method in previous video, you only have one u, one y. But now instead of one y, one u, you have two u, two y. And it's a one-to-one transformation method. So basically, the method is similar with previous. Okay. However, we will use a Jacobian, okay, to find the differentiation of the random variables or the function. Okay, so if the inverse function h1 u1 u2 and inverse function h2 u1 u2 have continuous partial derivative with respect to u1 u2, then you have this Jacobian j equal with determinant of this one. So you can see that the first column, the first quadrant, okay, you will differentiate partially with respect to u1, and then here you will differentiate with respect to u2 when you have the inverse function of h1. Okay, and then the below here, the third quadrant, you will have partially differentiate h2 with respect to u1, and then the other one here you will have second inverse, okay, with respect to u2, and then here you will have this one you should times minus this one. Okay, so you can see here this one, okay, you have this one, oh sorry, this one first, okay, this one first and then minus this one. All right, so I'll show you again here. Okay, after you get the partial derivative for each here, you will have this one times minus this one. Okay, and then this one should not equal with 0. All right, then the joint density of u1 and u2 is given like this one. Okay, this is the density function. Okay, and then times with determinant Jacobian, okay, which is absolute Jacobian. So important notes here, the absolute value of Jacobian in the multivariate transformation is analog to quantity inverse function of u with respect to du. Okay, if you remember in previous method, in a previous video for one variate only, okay, we have this one. All right, so here when we have multivariate, we will use Jacobian. That is used when making the one variable transformation of u equal to function y. Okay, and then be sure that the bivariate transformation u1 equal with this function, and then u2 equal with this function is one-to-one transformation for all value y1 and y2. And then the density function of the joint distribution function of y1, y2 is greater than 0. Now we look example 6.13, page 326. Okay, let y1 and y2 be independent standard normal random variable. So you can see that y1, y2 follow standard normal independent random variable. And then if u1 equal to y2 plus y1 plus y2 and u2 equal with y1 minus y2, and then both u1 and u2 are linear combination of independent normally distributed random variables. Okay, And theorem 6.3 implies that U1 is normally distributed with mean 0. Okay, so 0 plus 0 you get 0. And then variance 1 plus 1 equal with 2. So similar, if you have for U2 has a normal distribution with mean 0 and variance 2. So the question asks you, what is the joint density of U1 and U2? So here you can see, first you have Y1, Y2, and then you have another function, U1, U2, and this U1 is not only Y1 or Y2, it's a combination of Y1 and Y2, whereas U1, which is equal Y1 plus Y2, and U2 equal with Y1 minus Y2. Okay, so that's why we call it multivariate here. Okay, multivariable. So in order for you to find the density function for the joint density function for U1 and U2, first you should know the density function for Y1 and Y2. So here they say Y1, Y2 follows standard normal distribution. When they say standard normal distribution, that means your mean is 0, your variance square is 1. Okay, so when you substitute this one into the density function of normal distribution, you will get this equation. And your y2 is still in between negative infinity to infinity. And the independence of y1, y2 implies that their joint density is this one. So when it's independent, okay, in order for you to find this one, you will multiply y1 with y2. Okay, so that's why you get this density function, joint density function. Okay, next, okay, in the case the density function, the joint density function is greater than 0. So y1 is between negative infinity to infinity, and then y2 is between negative infinity to infinity as well. So we are interested in the transformation. Okay, so you have u1 just now, y1 plus y2. So this is a function of h1. Okay, this one. And then for u2, we have y1 minus y2. So this is the function of y1, y2. Okay, so in order for you to find the inverse function for this one, okay, you will have u1 plus u2 divided by 2. Alright, so how you get the inverse transformation method in here? Okay, first from the function above here, you have u1 equal to y1 plus y2. So let your y1 equal with, give y1, find y1 in term of u1 and y2. So here actually I can do y1 plus y2 equal to u1, and then I get y1 equal to u1 minus y2. Okay, so this is 1. From here, okay, you can have y1 minus y2 equal to u2, and then this one actually negative y2 equal to u2 minus y1. Okay, and then I bring the negatives to the side, so I will get y1 minus u2. So here is y2, you put inside here. So when you substitute here, you will get y1 equal with u1 minus y1 minus u2. So you break the bracket, u1 minus y1 plus u2. So here you can bring to the left, so you will get y1 plus y1 equal u1 plus u2. So here you will get 2y1 equal with u1 plus u2. Then y1 equal u1 plus u2 divided by 2. So here what you get for the inverse function for u1, u2. So similarly, you do the same thing like this for y2. Okay, then you will get the inverse function for u1, u2 for h1, and then the inverse function for u1, u2 for h2. Okay, because we have now two functions. And then you need to find the Jacobian. Okay, so if you look the Jacobian formula from the previous theorem, this one, okay, the first one is inverse function 1 with respect to u1. Okay, so you look here, here actually is this is your function, which is u1 plus u2 divided by 2. So when you differentiate with respect to u1, you will get half. Okay. Alright, if you look this, you differentiate partially. Okay, so this one actually is your h1 inverse, isn't it? So I write down like this, u1 plus u2 divided by 2. So when you differentiate this one with respect to u1, this one only. So this one actually you can break this down, u1 over 2 plus u2 over 2. So because you differentiate partially, you will differentiate this one as well, because with respect to u1. So here you differentiate u1, you get half. Okay, and then similarly for this one, you differentiate with respect to u2, you still get half here. All right, and then for h2, okay, this is the inverse function of h2. So you can see that you have u1 minus u2 over 2. So this one, if I break it down, u1 over 2 minus u2 over 2. So you can see that this one, you differentiate h2 with respect to u1, you get half, the same thing. And then this side, you differentiate u2 with respect, you differentiate h2 inverse with respect to u2, so you get negative half. Alright, so this is what you get, the Jacobian. Okay, then you find the determinant of this Jacobian, half times negative half minus half times half. So you get negative half here. Alright, and then we use absolute value only. Okay, that's mean half lah here. So in order to find the joint density function for u1 and u2, okay, with exponent this one, okay, so if you look, we will have from previous theorem, you can see that this is the formula. That's means you have density function. Here you will have h inverse 1 and then h inverse 2. So here you can have h inverse 1, h inverse 2. So here, this one. Alright. So you will have this one, but instead of y, now you substitute what is your y1 and your y2. So you can see that your y1 is this one, u1 plus u2 divided by 2 square. And then here u1 minus u2 divided by 2 square. This is your y2. When you substitute this one, and then times with the absolute Jacobian. Alright. So again, similar step you will do for the limit as well. Okay, so you have this one, you bring to the left to the right, then you will get the limit. So you simplify this one. Finally, a little algebra tu, you can have like this. Alright. So here actually what you have just now, okay, you simplify, you get this one. Okay, and then this one for the limit, okay. Finally, you get u1 is still between negative infinity to infinity, and u2 still also from negative infinity to infinity. And then because for pi, you have this one, okay. This one you must or you need to be creative in order for you to understand how to get this one, okay. Because we want to see this follow which distribution, okay. So that's why it can be break down like this, and it's quite similar with normal distribution function, okay. And then when you simplify and substitute, you will get this equation, okay. So you can see lah, it's still normal, alright, but you have different value of mean and variance, okay. So you can see that u1, u2 are independent and follow normal distribution, and with both mean equal to 0 and variance equal to 2. This one, okay, if you remember, this one actually sigma, isn't it? Sigma 2 pi. So that's why here sigma is square root 2, but the variance is 2. Okay, and then here you can see that usually we have u minus mu square divided by 2, isn't it? 2 sigma or sigma square. Alright, but here we have 4. So that's why we have 2. Alright. So here the extra information provided by the joint distribution of u1 and u2 is that these two variables are independent. Alright. Okay, so that's example. You can try do one exercise and then look. The step is similar like univariate, but instead of one, you have two function. And the difference here is at the Jacobian part. Okay, but actually it's still similar because of this note. Okay, so I think that's all for this video. Thank you, class.